Hi, in this video, we want to talk about Latin squares. All right, so our goal in experimental design is to get the most information possible out of our data before we collect our data. All right, so in design of experiments, we're going through and we're setting up our game plan to make sure that our data gives us as much output as possible. All right, so Latin squares is one of our tools in the tool belt to get information out. All right, so a Latin square is a method for us mathematically to get around two nuisance variables when I'm interested in a third predictor variable that is like a treatment or some other variable of interest, and then we have a response. So when we go through this, keep in mind that this entire time that we're talking about Latin squares, we're doing this before we've collected data. So what we want to do, we want to come up with that game plan to get the most bang for our buck. We want to squeeze out every bit of information from our data. So we're going to come up with a game plan before we actually start, getting our data in our hands. All right, so experimental design is a critical aspect of statistical analysis of research. A properly designed experiment can isolate the effects of a variable of interest, allowing for more robust and reliable conclusions. One powerful tool for experimental design is the Latin square, which can help manage confounding factors in an experiment. All right, so here, what I want to do, I want to start with a poorly designed experiment right out of the gate. And then I want to show how we can make things better with Latin square. Okay, so here, let's go ahead and look at this experimental design situation. So we have sex, we have side left or right, we have treatment, and then we have the response variable that is what we're wanting to study. So in this situation, we actually want to study the relationship between treatment and response. Response is the dependent variable. Treatment is the independent variable, okay? And so sex and side, in this situation, we know already, or we believe reasonably, that these two variables are related to the response variable. And like we already know this. We know this is a fact, but we're not interested in this. We don't want to study the relationship between sex and the response. We don't want to study the relationship between side and the response. And so what we're going to do, we want to set up so that with as strong of a signal as possible, we want to see the relationship between treatment and response, and we don't want side and sex playing a role in the output of our results. Now, let's take a look at the situation. Each row represents an observation. And so in the first row, we have a male. Treatment is on the left side, and they get the higher level of the treatment. And then here I put a question mark. Now, I want to put a question mark there for my dependent variable because I want to emphasize that our goal is to study the relationship between treatment and response, and we're doing this before we collect data. So I'm just putting a question mark there to make sure that as we work through this video, it's clear to us that we're doing this before we actually collect our data. What we're going to do, we're going to find a male, we're going to put the treatment on their left, and it's going to be the high level of treatment. Now, let's check out the next row. Well, once again, we're going to find another male, we're going to treat him on the left, and we're going to treat him at the higher level. This row, we're going to do the same thing again, and the same thing again. So in this situation, I have 4 males getting treated on the left with a high level of treatment. Okay. Now, the last 4, we have a female. She gets the treatment on the right, but it's at the low level this time. And then we do the exact same thing all the way across. And so I need 4 males, 4 females. I'm treating left 4 times, right 4 times, and the high treatment is given 4 times, and the low treatment is given 4 times. Okay, but look at this. Look at what's going on. Whatever's going on with our data, if let's say the ones with the males, we have a larger value for our target variable. We don't know if that's because of male or left side or the higher level of treatments. Like any effect that we have, I don't know if it's sex, side, treatment, or a combination of them. There could be an interaction effect going on. We don't know. We can't pick it up. So this is a poorly designed experiment. Now, something I want to take a moment and talk about is that when we come across poorly designed experiments, we should not make a make a fuss about it. We should encourage people to run experiments to collect data. Most of the time, poor experiments are better than no experiments at all. And because we can use poor experiments to just kind of get a feel for what's going on, get some intuition to guide us on better design studies down the road. All right, so here we have 3 variables, and if there is a statistically significant aspect in here, we're not going to know which of the independent variables or the combinations of them is leading to the results that we're seeing. And so this is not a very good experiment. All right, so let's go ahead and improve this. All right, for this one, what we're going to do, now you see that I've shuffled male and female down the sex column, but I've left side and treatment this way. All right, so now if you ignore side for a moment, you'll notice I have male and high, female and high. So at the high level, we have male and female equal number of times. So, and at the low level, we have male and female an equal number of times. All right, so what this is doing is that this is blocking the nuisance variable of sex. And so sex is blocked as a nuisance variable, but side we haven't fixed. So I'll never be able to tell, is it side or is it treatment, or combination of them is resulting in my results. And so I can't fully distinguish this. Now, this is better. This isn't as bad as what we had before, but we can do better. So what I want to talk about for a moment, just a moment, and we'll get deeper into this in a future video. I want to use a full factorial design. All right, so what we're going to do is with sex, there's 2 levels. With side, there's 2 levels. And with treatment, there's 2 levels. 2 times 2 times 2 is 8. All right, so what we're going to do, we're going to look at all 8 possible combinations of sex, side, and treatment. And we're going to collect a data point from each of them. And then we're going to look at our response variable. And so here, this is a really good situation that I'm going to be able to really see what's going on with the treatment. That is what I'm actually interested in. And so this is called a full factorial design. And this occurs when I look at all possible combinations across all of my factorial variables. And so this is a good, well-designed experiment. If I can run this, imagine the situation where each row of data was super expensive. All right, if each row of data was super expensive, 8 might not be in the budget, or maybe it takes a long time to collect it, and I just don't have the luxury of collecting 8 data points. All right, so full factorial designs are awesome. They're great, but when we have a lot of factors to consider, or factors with a larger number of levels, here we have 2 for male and female, 2 for left and right, 2 for treatment and high and low. So we don't have that many levels to worry about. If, let's say, I had 5 levels on one, 10 on another, and 16 on another, then that's a lot more, a lot more observations I have to collect, and it may not be feasible for me to do that. So what we want to do, we want to figure out a way to get as much information from our data with as few observations as possible. And so we want to get good solid data with as little effort and resources as possible. So what we're going to do is we're going to use a Latin square. All right, so what I'm going to do, actually, I'm going to scroll down for a little bit. I'm going to skip for a moment. I'm going to show you the experiment matrix. Now look at this. Now this is better than the first two experimental designs that we had previously, believe it or not. Now, in this situation, I'm only collecting 4 points of data, but this would actually be a better experiment than the first two experiments I showed you, especially that first one. You'll notice I've got male, I've got left, and I've got high. I've got female, left, and low. I have male, right, and low, female, right, and high. So you'll notice that with sex and side, all possible combinations are present. With sex and treatment, all possible combinations are present. With side and treatment, all possible combinations are present. Okay. And so what's going on here is that on the main effects, remember from our ANOVA main effects, on the main effects, I've got all possible combinations manifested. So this is a good situation for analyzing the main effects. So only with 4 data points, I've actually got a better situation than with the 8 I had previously. Now, how do I figure out what is the combinations I want to have? We're going to use a Latin square. All right, so this is like the data frame version of our experiments. The Latin square version is going to be here. And now why is it called Latin square? Because back in the day when they first started talking about this, they used Latin letters. That's why it's called Latin square. All right, so what we're going to do on our nuisance variables, the variables that we're not interested in, we're going to have those correspond, like each row is going to correspond to a level of the first nuisance variable. The second row corresponds to the second level of the nuisance variable. The first column corresponds to the first level of the second nuisance variable, and the second column corresponds to the second level of the nuisance variable. Now, what we're going to do is we're going to make sure that each row and each column has every possible level of the variable that we're interested in, the independent variable that we actually want to study. We have every single level of it, high and low, in every column, and we have high and low in every single column. All right, so, and that's how we set this up. Now, after I have this presentation, what I need to do is I need to reshape my data. There's a couple of different ways to do it. I choose to use gather. This is a depreciated function in the tidyverse. I prefer to use it because it's the one I use. You know, the one I learned first. I'm old. I don't like to update. And so I went ahead and used the gather function. Oh, and I made a mistake. Not a big mistake, but I wanted this as a data frame on the bottom of that. This is actually a useless step in my piping. But now, when we use Latin square, something that's interesting about it is that if my treatment has 5 levels, then I need to have 5 levels for both of my nuisance variables if it's a true Latin square. Now, there are modifications that we can achieve that are in like certain R packages that will take care of it for us. We'll look at the package in a moment. But for the time being for this video, if I have 5 levels of my treatment, I need 5 levels for both of my nuisance variables. If my treatment level has 10, if I have 10 levels for my treatment predictor variable, then I need 10 levels for the first nuisance variable. I need 10 levels for the second nuisance variable. And that's because it's going to be a square. Now, there are ways to address the situation where we don't have such a perfect jive with a number of levels, but I'm not going to worry about that for now. All right, so let's talk about generating Latin squares with R. All right, so I feel like the Agricole package is a good choice for generating Latin squares. There's a couple of different ways to do it. I felt like this was the easiest way to go about it. Now, the function we want to use is design.lsd. So that's Latin square design. And then the treatment, we specify the vector of the treatment. And in this, what we want to do is, R will automatically assume that we have whatever the length of this vector is, it will assume that we have that many levels for both of our nuisance variables. Now it uses a random number to generate the Latin squares. There are a lot of Latin squares possible, and there's different ways to generate. And the default one is super duper. I thought it was just kind of funny to see super duper, so I went ahead and printed that on there. And so when we get our Latin square, there's a whole bunch of stuff that's put out, but you can see this is the actual Latin square. The rows correspond to the value of the first nuisance variable. The columns correspond to the values of the second nuisance variable. And then each cell entry indicates the value of the treatments. And so here we have 3 different levels of treatments. And now to look at that in a reshaped manner, we just go ahead and use the book slot of the output. And this will work it all out for us. And so here we can figure out what's going on the main effects aspect of our analysis. Now, something that I find really exciting is that there is a connection between group theory and Latin squares. All right, so if you don't know, my doctorate's in mathematics, not in statistics. I studied abstract algebra up, down, left, and right deeply in school. And I feel very passionate about abstract algebra. And so I get absolutely giddy when group theory kicks in. And University of Florida had a really, really strong group theory program when I was there. And I had to learn it very, very deeply. So I get pumped up. All right, so there's a connection between Latin squares and group theory. So if we take the Cayley table from a finite group, so that is a group with a finite number of elements in it, and a group has an operation, it's closed under that operation. We have the identity elements, we have associativity, we don't have to have commutativity, and there will be an identity. If a billion group will have commutativity. We don't need it for this purpose. But every single Cayley table that's coming from a finite group is going to correspond to a Latin square. Okay, so why is this important to us as statisticians? Well, if I would need to generate a Latin square and I can't get software to do it, I could potentially use group theory to generate the Cayley table. Now, what is a Cayley table? Cayley table is a multiplication table for something more complicated than regular multiplication and addition. It's a comprehensive multiplication or addition table for groups or rings or whatever. Now, something that's unfortunate is that not every Latin square corresponds to a Cayley table. Therefore, a Latin square does not necessarily correspond to a finite group. So if it's a finite group, I can always get a Latin square, but a Latin square I may or may not be able to connect back to a group. Now, Sudoku tables, the puzzle with a 9x9, the solution of every single Sudoku puzzle is actually a Latin square for 9 treatments, or treatment with 9 levels, and nuisance variables with 9 levels. All right, so Latin squares are a powerful tool in experimental design. This is an efficient and effective means of managing confounding variables in our experiments. And also they're just interesting and fun because they pull in group theory, and we can take a look at them in a puzzle off of any puzzle book in a grocery store. All right, well, that's all I've got for you. Life is short. Do math.